That. So I just want to say a couple of quick things. First of all, thank you to those of you that were able to get on there and to watch those things. If you worked on things and you have questions, let me know. I know that things were a little bit muddled as I walked through that. I was kind of trying to manage my children and get all information to you at the same time. There were 3 problems at the end that involved some kinematics and some Newton's second law stuff. I will put up solutions to those. I have not written up the solutions yet, but I will write up solutions this weekend and put those up so that you have access to them, okay? But we are not going to spend time in class going over that, okay? We just do not have the time to do it. I wish we did, we just don't. If you watch the videos and look at the problems and you're still stuck, please come in and chat with me, okay? I am here during Liberty time all the time. You can make arrangements to come see me pretty much whenever else you want, except at least next week when I'm teaching AP Physics, because Mr. B's got the rest of it covered. So you let me know, we'll sit down and do physics, okay? I want to do it with you. I want you to understand it. We don't have time to do it in class, okay? The big thing that I'm hoping that you took away from yesterday when you were watching things was that different objects, non-point mass objects, have different moment of inertia calculations, okay? The reason for it is because of the makeup of the mass about the axis, okay? So for example, you've got this rectangular plate with an axis through the center. So this would be like the whole thing is spinning around like this, okay? You take that same rectangular plane and you start rotating it this way. And now the axis of rotation, because the axis of rotation has changed, the moment of inertia has also changed, okay? My friends that are in calculus probably understand the idea of adding the little bits together to get these values, but you do not have to understand that for this course. What you need to know is that different objects have different moment of inertia calculations depending on where the mass is relative to the axis of rotation. That's what you need to know. And if given one of these, you need to be able to embrace it, use it, and understand it. Okay? Questions that you have about that piece? Does that make sense-ish? Okay. If you're not so sure, take some time this weekend and go back and take a look at it so that you're okay. Today we are going to move on. According to Canvas, we were supposed to do start a lab today and finish it on Monday, but because of the late start and the super short period, I'm going to wait and we'll do that Monday, Tuesday. It just feels better to do that, so I want to do some in-class content today. So here we go. We're going to go ahead and get started with a warm-up problem that will look pretty familiar to you, but I want you to revisit it real quick. It's been a few days since you've looked at it. Go ahead and pull a piece of paper out because you're going to need paper out as we go through today. So go ahead and take a couple of moments to take a look at this question, to remind yourself of what was going on, and then we will discuss. Yeah. All right. Let's take a look at this problem, shall we? So, Chris, what was the question that you asked? Same mass. I know I'm frozen. Hold, thank you. I just wanted to write this down so I didn't forget. Do they have the same mass? I don't know. Chris, you've decided it doesn't matter? Okay. All right. So there are 2 questions that are being asked. One is which rider, Paul or Kathleen, is traveling faster at the bottom. The second is which rider makes it to the bottom first. Which one do you want to start with? Sid, which one do you want to do first, A or B? Let's go with A. All right. Which rider is traveling faster at the bottom? What do y'all think? Shall we vote? I'm throwing it out to anybody, whoever would like to answer. You want to vote? Chris is calling for a vote. Is that okay? All right. So here's the question. Which one is traveling faster at the bottom? Raise your hand if you think it's Paul. Paul is going faster at the bottom. Raise your hand if you think it's Kathleen. Is she the only person that voted? Sid, you asked for question A first. Oh, you think there's another option? What option do you think is the right option? What option were you waiting for? Same speed. Speed also. Yeah, and why? I don't know if they have the same mass. What if they don't?
If they don't, then the kinetic energy is the same.
Okay, we got to be careful here. So you're saying, I'm saying, I'm going to make an assumption just for fun that Kathleen has a bigger mass than Paul. Okay, if Kathleen has more mass than Paul, you're telling me that they. So let's talk about this, you guys. So I'm going to make an assumption. Whoa, hi. That's not helpful. Assume that the mass of Kathleen is greater than the mass of Paul. Okay. If that's the case, Sid, you're changing your story. Is that right or no? Maybe you're not. I don't know. I'm not trying to put words in your mouth. So tell me why not. That's okay. And you can say that you want to just pass that on to somebody else. Josh has got it. Go. Kinetic energy and the force of gravity depend on mass. The masses cancel? Okay. I'm not saying you're right or wrong, but I'm saying if this was the explanation on a test problem, I would not give you credit for this because I don't understand what you mean. Does that make sense? So I'm not saying it's wrong. I'm just saying this would not get the points for being well reasoned. So tell me more words. Okay. Okay.
We know that potential energy at the top.
Okay.
Have the same height.
Whoa, hello. So the gravitational potential energy. Okay, keep talking. Mm-hmm. 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 You guys following what he's saying? Elena, how are you feeling about that? You sure?
Well, I didn't really agree with that. I thought that probably the change in height was something about much higher height.
Kathleen. I think that they're actually both starting right up here. Yeah, this is just part of the story. So, okay, so let me back up for a second. And let's answer the question that Elena was just answering. Is that okay? As a group, to make sure that we're all. So if Paul starts here and Kathleen starts here, and this is the beginning of the story in both cases. In that case, for that situation, right where we're at the beginning here, in that case, if the start is here, who's going to be going faster at the bottom? Paul is. Do we all agree on that? Okay, that's cool. Now, does the shift of the question make sense? If we're looking where the star is, that's where like they all walk up to the top steps and then have somebody go one way. Yeah. So if they start here, and this is just partway through their story, then does what Josh is suggesting jive with what you know for physics? Yeah. How are we doing here, friends? This seems to make sense to me. This right here is the piece you have to have. right? This right here is what? What's that a statement of? Conservation of energy, right? The total energy at the top is equal to the total energy at the bottom. That's the reasoning that leads us to this. We have to make sure that we're marking that this is the mgh at the top and the 1/2 mv squared at the bottom. And then I think if I caught what Josh was saying, then the mass here and the mass here go away. So this could be a story about Kathleen, or it could be a story about Paul. Doesn't matter. If their height is the same, then their velocity is the same. And again, if we interpret the picture the way that Alana interpreted the picture, where Paul starts out higher, I appreciate the fact that you said that, honestly, because it gives us another situation to look at. So it's awesome. If we look at the situation where we're just starting where the picture shows, then indeed Paul would have to be going faster because he starts out at a higher height. Right? Okay, so that was part A. We answered that one. Which one's going to make it to the bottom first? Are you ready to vote on that one? Or do you want to discuss for a minute? Or do you have no idea? I can't read your faces, you guys. Holy cow. It's like you're all like made an agreement, like, do not answer Miss Carbling's question this time. Do you do like hide your face and vote thing? Is that what needs to happen? Okay, you take your right hand. You're like, man, I didn't, yeah, take your right hand and put it over your eye. Right hand over your eye. Okay, you're gonna put your left hand in the air. If I see you peeking, I'm gonna be really crabby. All right, so the question is, which writer makes it to the bottom first? Raise your hand if you think it is Paul. Paul makes it to the bottom first. Raise your hand if you think it is Kathleen. Kathleen makes it to the bottom first. Raise your hand if you think that they're going to get there at the same time. All right, hands down, eyes up. I will tell you that there were votes for all three. Okay? So we got to figure it out. All of you voted, I think. I think that I saw that there weren't any abstainers. So somebody make an argument for me. Who gets there first? You all voted, so you all have an opinion. Help me out, you guys. We have lots to do today. Go, Josh.
I said Kathleen because I don't really have that solid reason, but she's going faster earlier.
Okay.
She, over time, she's going to be further in less time because she starts going faster earlier than Paul.
Okay.
And Paul has to start off really slow.
Go. You had something you wanted to throw in there, Shushi. What did you have?
Even though he doesn't go as fast as he won't be going. When she is like where she is right now,
Uh-huh.
he'll be going faster.
At that place right there? Is that what you said? You don't seem super confident. But it's like you want something to be true. Is that true? Okay. I'm not positive that I know exactly what you're arguing, so I'm going to try and draw it out. Is that okay? Can I play it a little bit? Okay. So Paul starts, at this point here, what kind of energy do we have? Do both people have? Just potential, right? Gravitational potential, that's it. Right here, do either of these people have potential energy? They both do have some. Who has more potential energy? Paul does. Does that make sense? Why? He's higher up, right? MGH, the higher you are, the more gravitational potential you have. So Kathleen has less gravitational potential, which means she has more kinetic, which means right here, who is moving faster? Kathleen, does that make sense? If the lower that you are on that process, like on that slide, the faster you're moving. Is that okay so far? Okay. So if they're moving, if Kathleen's moving faster than Paul, then if we look at it kind of going over across this way, for all of this part, like from the star to the green, Paul isn't moving very fast. Are you with me there? Whereas Kathleen, like right about here, she starts moving pretty fast. Would you agree? So for like this part of it, Kathleen's moving pretty fast. Paul's moving not so fast. Now, when he comes over here, is that what you were thinking? Like, oh my gosh, right here, like, whoa, I do not want to ride this slide, not gonna lie. Like, I'm like roller coaster, that sounds really scary to me. Right? Ooh, that would be really scary. He's gonna accelerate a lot. But she has already been moving fast for a long time. Does that kind of make sense? It feels weird. But who is moving faster at the bottom? Down here, who's moving faster? Same speed. We just said that earlier, right? Same beginning height, so same speed at the end. So moving the same speed here, it's just that Kathleen starts moving faster sooner. Does that make sense? Is that okay? And if she moves faster sooner, she's going to cover more ground in this like X direction in any given time than Paul will. Is that okay? Does that kind of make sense? So, Josh, yeah, I would agree. Yes, it is Kathleen. The good physics reasoning that you were kind of saying, but you weren't feeling very confident about it, is just, I mean, it's basically what you said, right? That Kathleen, she moves faster sooner or for a longer time, right? And so they're going the same distance in the X direction, but she's going fast for more of it than Paul is. And if you're going fast for more of it, then you're going to win. Yeah. Now, Chris, I wanted to wait to ask this question until you came back because I heard you and a couple other people say it early on in the story. So I'm going to ask one more. It's part C. Which rider has more kinetic energy at the bottom? Paul, Kathleen, or are they the same? If Paul is smaller than Kathleen, who has more kinetic energy at the bottom? Kathleen. So the distinction that I want to make there is even though they both have all potential up here and all kinetic down here, the amount of kinetic that they have or the amount of potential that they have up here is dependent on their mass. Say words out.
I thought it was because she was going faster, so it's the V squared.
Is she going faster at the bottom?
Oh, no, she's going faster here.
That's true.
But our matches, their matches aren't given, so how do we know? Are we just saying that we're just?
I'm saying if Kathleen was bigger.
Yeah.
But the distinction that I want to make, and it's not obvious, but it's really important. They have the same height at the top. They have the same velocity at the bottom. But Paul and Kathleen don't necessarily have the same potential energy at the top or the same kinetic energy at the bottom. That's dependent on their mass. Okay? How are we doing? That conversation is a repeat of the conversation we had in October. Yay for us. Okay? Now we're going to go have another conversation. I'm going to pause the video for my friends at home, and we're going to go take a little walk over to the other side of the room. All right. So for our friends at home and for your notes, we need to write down what we observed. So we had a ramp. I am recording this for our friends that are not here today, right? So we had a ramp, and on that ramp we had a round object. It was either a disc or a hoop, one of the two, okay, or a ring, I guess is how I have it described. And I'm just going to write them down so we can pair them off and know what happened. So we had the ring versus the small disc And then we had the small disk versus the large disk. So the first question is, when you had ring versus small disk, who won? The small disk won, yes. When we did the small disk versus the large disk, who won? The small disk won again. So that's the observation part of it, but the physicist part of it, the thing that I'm asking you is, why? I don't want to break your heart, but it has nothing to do with friction. Okay, okay, go.
The ring,
Okay,
it's got all its mass really far in the center.
it does.
So its moment of inertia is either bigger or smaller. How does it? It's larger, yeah.
Right, so let's just remind ourselves of this, right? So moment of inertia has to do with m and r squared, right? And sometimes there's a fraction in front, depending on how the calculus works, whatever. But the bigger the mass, and the bigger or the further out that mass is, the bigger the moment of inertia. So the ring has a larger I than the small disk, okay? Right.
But it has less mass farther away. The mass is closer to
Are we doing ring versus small disk still, or did you? Okay. Yes. Yes. So the ring versus the small disk. The small disk won because it has a smaller moment of inertia, right?
Yeah.
Yeah. So it's much easier to get it to rotate, right? It's easier to get it to rotate. Talk to me about small disk versus large disk.
the largest has big radius.
It has a big radius and it has a big mass, right? So in both of those cases, again, the large disk has a larger moment of inertia. And so a larger resistance to rotation. Okay? The moral of the story here is, what do you need in order to win this race, this rolling race? The smallest moment of inertia possible, right? Yes, yes. Smaller I wins every time. So this game, you guys, is very similar to the stuff that we had been doing before with Paul and Kathleen, right? So we can define the kinetic energy transfer from potential energy, because in each of these cases, that thing that was rotating at the top here has just gravitational potential, right? But as it rolls, what happens to that gravitational potential? It goes down, doesn't it? And it doesn't just go into nowhere. What does it turn into? Kinetic energy. But is it only in nice, happy translational kinetic energy? Not anymore, because the whole idea here was that the thing that mattered, because if I had two blocks on a frictionless surface on the same track, who's going to win? Who's going to get there first? Good question. If I look at this picture and I put both Paul and Kathleen on this slide, on Kathleen's slide, and Kathleen is a lot bigger than Paul, who's going to win? What? Same time, right? Same time. Now, this is the same track. So it seems like they should get there at the same time, right? That's what we've been talking about this whole time, but in this case, no. In fact, one got there first. So we need to define something. We're going to write it down right now. Here we go. We've got this thing that we call kinetic energy, don't we? 1/2 mv squared. But here's a secret, friends. It needs a sub T for translational. That's what we know, love, and understand as translational kinetic energy. You remember from earlier this week that V is equal to omega times R. So now we can write K equals 1/2 m times omega R quantity squared. We can write this as 1/2 mr squared times omega squared. And what's mr squared? I. Here's the thing I want you to know. I am going to post solutions to those problems from last night or from yesterday. I am also going to post a video with some more stuff with this on it as well. I will get them done by tomorrow morning. I will stay up tonight and finish them, okay? Please make sure that sometime this weekend you watch that stuff because we just don't have a lot of time because the trimester end is coming fast. We got to get stuff done, okay? Have a very happy Valentine's Day. Take those Valentines with you. Share them with your Valentine. Awesome, I love it. Have a fantastic weekend, you guys. Be well.